Today we shall discuss about the polymer composites. To start with, let us think of the gift of nature. What kinds of composites have been gifted by nature? Number one, nature gifted composite is wood. Wood is a composite of cellulose and lignin. Cellulose is the reinforcement or dispersed phase, lignin is the continuous phase known as matrix, and because of that reinforcement of cellulose fibers as fibers in molecular level in the lignin matrix, which is also of very high molecular weight in wood. Wood is a very strong material available in nature from plant origin, and by virtue of that composite characteristics, the branches of a big branches of a tree can bear such load as cantilever. From this naturally occurring composite, we can understand the load bearing capacity of composites. Second example of nature's gift is animal bone. It is, we can also consider this animal bone as another natural composite from animal origin. This bone is a composite of hydroxyapatite. In brief, we can write HAP, whose formula is, it contains 10 calcium, 6 hydroxyl groups and phosphate. Okay. So, this is the calcium hydroxyapatite, this is the bone mineral remaining as dispersed phase in a continuous phase called collagen as matrix. Collagen is the matrix and this hydroxyapatite is the dispersed phase. Looking into this natural bone, people have tried to mimic this natural bone and developed artificial bone, and in case of bone injury, broken bones are being replaced by artificial composites prepared from this dispersed calcium hydroxyapatite in some synthetic polymer matrix, that may be collagen or some other biodegradable polymers like polylactic acid or even chitosan. So, these are artificial synthetic composites are used in being used in biomedical engineering as biomedical implants. There can be other synthetic composites, these are two natural composites. There can be other synthetic composites, we find their frequent use. One is roofing sheet, say known as asbestos sheet. Asbestos sheet, which is actually made in the form of corrugated sheet. These corrugated sheets are used for roofing purpose to protect from rain and sunlight. This is a strong composite. The strength is contributed by the presence of asbestos fiber in dispersed condition in a cement fly ash combined matrix. So, this asbestos sheet is a good example of composite of inorganic character, whereas wood is a composite of organic character, and animal bone is a composite of inorganic organic character. So, here we find that the matrix, there are two different phases, one is the continuous matrix phase and the other is the dispersed phase known as reinforcement. We come across another huge composite, all of us well known to such composite, that is RCC, reinforced cement concrete. What is this? This reinforced cement concrete, we know that in this RCC steel rods are used as reinforcement or dispersed phase in a continuous fiber form, continuous rod form, which remains embedded in a continuous phase known as cement sand mortar, and there is another dispersed phase, that is stone chips. These steel rods and stone chips are embedded in sand, cement, mortar. After setting, it gives a very strong composites, out of which we prepare huge building structural bodies, like say huge building, bridge, so and so. So, these are few examples of composites where we find there are two different phases, one is the continuous phase and the other is the matrix phase. To start with, so we can define this composite as a combination of individual components of matrix phase and reinforcement phase, and both these individual components have contribution to the properties of the final component, although we find that either of these components are not that strong, whereas that of your composites, strength of that composites. So, composite is very stronger than the either of the component phases like matrix and reinforcement. If we look into the classification of this matrix or matrices in plural form, we find there can be polymer composites, there can be metal composite, there can be ceramic composite, there can be carbon and graphite composite. That means, we can use any type of matrix or continuous phase using a suitable polymer, using a suitable metal, or using a suitable ceramic material, or even carbon and graphite. Why these are? Why such matrix different matrix materials are necessary for making composites? Because we have to think of the purpose for which such composites are being made from the point of view of strength, ultimate strength, rigidity, stiffness, their stability, their response towards temperature extremes like low temperature, very low temperature, say cryogenic temperature, or very high temperature, like even it can, some composites can go beyond 2400 degree Celsius without any loss in properties. Now, this carbon and graphite matrix composites can go to that extent where this carbon matrix or graphite matrix do not decompose. In fact, such matrix is prepared by taking a porous precursor, carbon precursor, taking a precursor into which carbonaceous fluid is impregnated into that porous precursor, then it is pyrolyzed in inert atmosphere, where this carbon or graphite formation occurs and it becomes a matrix, good and strong matrix, and which can stand very high temperature. You know, ceramic materials are also very high temperature material. That means, the ceramic materials can withstand very high temperature without loss in properties, although it is brittle in nature. Metal matrix composite can also be there, where very high strength performance is required, one can go for metal matrix composite. And polymer matrix composite, where it may not provide very high temperature resistance, but it is very good matrix material for common or general purpose composites, and by virtue of some special features of polymer, starting from their low specific gravity, their easy processability, good tailorability, and good resistance to corrosion, other things, this polymer matrix can become a very good choice for making composites. Now, within the class of polymer, which is the subject matter of our discussion today, this within the polymer there can be of two major categories, one based on their response to thermal environment. One is thermosets type of polymer, and the other is thermoplastic type of polymer. Now, in these thermoplastics, they behave like this. The thermoplastics can soften on heating and it hardens on cooling, and this process is reversible, whereas thermosets, it softens on heating, but gradually it undergo some chemical reactions and it forms a three-dimensional cross-linked network bonds, and ultimately it becomes rigid and strong and permanent, which cannot be reverted back to the initial condition. So, it cannot be softened further on cooling after cooling. That means, once a thermoset structure is formed by heating, then on cooling such thermoset structures become solid and rigid, and such rigid and solid structures cannot be softened, or it cannot become flexible after further heating. Within the thermoplastic category of polymers, there can be several examples, several polymers available. There is huge versatility of finding this thermoplastic polymer matrix for making composites. We can start with say polyethylene, polystyrenes, polypropylene, which are polyolefin polymers, purely hydrocarbon polymers, and which are thermoplastic in nature, and other categories are say nylons and or polyamides. Now, nylons, they are condensation type of polymers, these are polypropylene, polystyrene, polyethylene, they are addition type of polymers. So, these are the in general these are the categories of polymers, thermoplastic polymers, which can be used for making used as matrix resin for making composites. Now, in the thermoset category, we can have epoxy polymers. Epoxy polymers are made from bisphenol A and epichlorohydrin by reaction of epoxy bisphenol A and epichlorohydrin, and epoxy polymers are good in one sense from one angle, that these polymers can be processed or can be applied, or these composites can be made from this epoxy polymer at room temperature, and slowly at room temperature it converts to a thermoset product this epoxy polymers. You know, there is example of Araldite, which is a commercial adhesive. It contains two pack, it is a two pack system, one is the resin and the other is the hardener, and when this resin and hardener after mixing in a proper ratio, then slowly it starts reacting to form a 3-dimensional cross linked thermoset product, and it becomes ultimately hard, and for this reaction it takes around 12 hours to 24 hours, which can also be further this your curing time can be, or reaction time can be decreased by application of heat, and for that also some cross linking system or curing system could be different. Another thermoset category is the unsaturated polyester. Now, this polyester, say polyethylene terephthalate, that is a thermoplastic material, whereas unsaturated polyester, that means polyester containing some unsaturated moieties, unsaturated functional sites, that undergoes slow cross linking reaction, so that it leads to a thermoset product. So, that thermoset unsaturated polyester is also used for making composites as a matrix resin. Phenolic resin covers a good volume of this composite industry. Phenolic resins are basically a condensation product of phenol and formaldehyde in different proportions. So, these different proportions make several grades of these phenolic resins, leading to a wide spectrum of properties of the polymer as well as the composite in which this phenolic resin was used as matrix resin. Polyamide resins, polyamides are basically, it can be aliphatic polyamides as well as aromatic polyamide, having that CO-NH or amide linkage. These polyamide resins are actually basically polar polymers, and by virtue of these polar groups they undergo several hydrogen bond interactions, intermolecular hydrogen bond interactions, and that lead to very strong matrix bonding and leading to very strong composite. Now, let us look into the dispersed phase. This dispersed phase means the reinforcing materials. What are the reinforcements? Now, reinforcing materials, again there are huge examples, huge materials available which can be put inside a matrix continuous phase to form a composite. Now, these reinforcing materials can be in the form of fiber, in the form of filler, say particle filler, in the form of whisker, in the form of flakes, in the form of particulates, or directionally solidified eutectics. Now, you know the your configuration, shape, dimension, etc. of these different kinds of reinforcements in reinforcing materials are different. The geometry they are having their different geometries. Now, fibers can be again many natural fiber, starting from natural fiber. One can have synthetic fibers, different kinds of synthetic fibers. Again, those fibers can be continuous fiber or chopped fiber. Again, those fibers can be used for making rovings, fabrics, clothes in different forms. Those fibers are used for making composites. In the field composites, this particle field composite, there can be particle field composites as well as those particles may be in the form of solid particles or in the form of microspheres. Again, these microspheres are solid and hollow. So, this way we find a good range of materials available for making composites from such dispersed phase. One good example I can tell, that is in particle field composites, say automobile tire. Automobile tire, the wheels of cars or vehicles. Now, these are made of rubber filled with carbon particle. Known as carbon black filler. Their particle size can range from say 30, even less than that, 13 nanometer to 300, 400 nanometer, like this. There are several grades of these carbon blacks which are incorporated in rubber matrix, a natural rubber or styrene butadiene rubber or polybutadiene rubber or a combination of natural polybutadiene, natural styrene butadiene, etc. When this carbon filler is incorporated and dispersed semi homogeneously, or you can say uniformly, this amount of carbon black in say 40 to 45 to 50 volume parts or parts by weight that can increase the strength enormously. So, that is why we get such load bearing capacity of such carbon black filler loaded tires. That is a composite of rubber and carbon black. Now, if you look into the different types of fibers which are used for making composites, say aluminum oxide is a good example of fiber, it is a ceramic fiber, aluminum oxide. Similarly, we can have boron fibers, carbon and graphite fibers, glass fiber. This glass fiber can be drawn in very thin dimension, then silicon nitride fiber, titanium carbide fiber, tungsten carbide fiber, zirconia fiber. Now, these are ceramic fibers. Apart from these ceramic fibers, there are some organic fibers, say polyolefin fibers can be available, aromatic nylons, aliphatic nylons, polyesters. So, that means different types of nylons, polyesters, polyolefins, say polyethylene, polypropylene, these fibers are used as a continuous fiber or chopped fiber as reinforcement material or dispersed phase in composites. Now, one thing we should consider at this point of time, here you see the chemical nature of these fibers are different, and in order to have a very strong composite, we must keep one aspect in mind, that is the adhesion at interface. Of fiber and matrix. Now, for this adhesion, for a good adhesion to obtain, there must be some chemical similarity between the dispersed phase and the continuous phase. Then only a miscibility or a compatibility will be available, and there can be some physicochemical bonding between the fiber and the matrix, that is what is required. Now, if such type of similarity is not there, then there will be separation into different phases, fiber phase and the matrix phase, and in that case when a structural component made of such composite will be loaded, the load will not be transmitted from fiber to the matrix or matrix to the fiber, and the interface region will be weak region where the stress will be concentrated at the interface region and the composite will fail. So, we have to think of selecting a good reinforcement which is strong as well as a good matrix which is also strong, but when such two different dispersed and matrix phases are used for making the composite, after forming the composite is supposed to bear huge load, that means the load bearing capacity would be much higher than that of the component reinforcement and matrix phases. In order to get that, we have to have very good interface adhesion, provided they have some chemical identity. Now, if you think of using aluminum oxide fiber in say organic matrix like say polyolefin, say polyethylene, that cannot be a good pair of your dispersed phase and the continuous matrix resin phase. That composite cannot be a strong composite. Whereas, if some nylons are used for as the fiber in polyolefin, that can be a very good composite. Say in case of fiber reinforced polymer composite, for example, glass fiber reinforced polyester GRP. Now, here polyester being a polar polymer having this ester group, in this polymer along with some other aliphatic groups like this CH2 etc., or aromatic linkage like this aromatic ring, some organic portion and polar portion having due to this oxygen, they can have a good interaction between the components of glass. Say glass contains SiO2, silica, and other oxide materials. Say there can be some little bit of sodium oxide depending on the what kind of glass it is, some magnesium or boron. So, say borosilicate glass in which boron will be there. So, glass is a oxide material. So, with this oxide material this polyester can have a good interaction and that can be a very good composite. So, glass fiber reinforced polyester, say unsaturated polyester or even polyethylene terephthalate, that gives a very strong composite. So, we have to have a judicious selection of this fiber reinforcement for one suitable matrix material, so that one can get a good composite. Now, if you look into typically used fiber resin pairs, which are successful pairs for making good strong composites, having very good interfacial addition, interfacial interaction, and they lead to very strong properties apart from their component properties of the component materials. Say alumina fiber reinforced epoxy is a good pair, aluminum fiber reinforced polyimide. In these cases, you see it is obvious that alumina Al2O3, that fiber, and epoxy polymer that also contain oxygen. Epoxy polymer is basically a polymer of bisphenol A, bisphenol A other side this group is. So, this bisphenol A, here you see the oxygen is there, this oxygen is epoxy group is there. So, this leads to very good matrix material for alumina because of the presence of this oxygen atom there. So, polyimide nylon having CONH group and alumina good combination, then boron fiber or carbon fiber in epoxy matrix, there is also another good combination, boron epoxy, boron polyimide, carbon acrylic. Acrylic polymer means say polyacrylonitrile or acrylate polymers, polyacrylonitrile pan polymer, polyacrylonitrile having this is the polar side, polyacrylonitrile or some acrylate, say PMMA, like this, or other copolymers or other derivatives. So, by virtue of these oxygen atoms or these groups or this COO group, AO group and or this CN group, these are polar groups, that can be a very good combination for composites. So, this carbon polymers, glass epoxy, glass carbon polyester, glass polyimide, glass silicone, nylon epoxy, and carbon acrylic as I was telling, and carbon epoxy, carbon nylon epoxy. Carbon fiber that is basically a graphite fiber. A carbon one can have as matrix material or a fiber material. This carbon fiber is made from this pan precursor. This is the polyacrylonitrile. Now, this polyacrylonitrile precursor is used for making carbon fiber. This CN group cyclizes with the adjacent methyl linkage. After cyclization, gradually when it is heated, it cyclizes, heated in inert atmosphere, it cyclizes and these hydrogens are expelled out, and then it forms a hexagonal graphitic structure. So, that is become stable, that is stable as well as strong. So, that carbon fiber is used for making high performance composites, which can stand very high temperature as well as very strong. Different types of glass fibers which are used for making such composites. There are different categories of glass fiber: C glass, which is chemically resistant glass, E glass, and this is the typical glass fiber, and these are used for making some having good electrical properties, and this R glass, which is R glass and S glass. These two different categories of glass, R and S glasses, are stiffer and stronger than E glass. Now, in polymer matrix composites, the matrix resins are supposed to certain functions, like they provide uniform distribution of structural and environmental load to the fiber through a good addition, as I was telling, to and strong interface with reinforcement. That means, the requirement is a very good addition of the reinforcement to the matrix, so that the load will be transmitted, distributed in a structural component, structural body from the fiber to the matrix and matrix to the fiber, so that no weak site is created at the interface region for stress concentration and ultimate failure. This polymer matrix also, apart from load bearing characteristics, they also protect the surface of the composite against abrasion, wear and tear, as well as corrosion, all of which can initiate fracture. So, this corrosion, wear and tear, abrasion, so these can initiate some weak zone, weak point or weak site where stress will be concentrated and failure can occur. So, this polymer matrix gives protection to all such drawbacks, shortcomings. Now, they absorb also the impact load and minimize stress concentration by enhancing the fracture toughness. This now actually this matrix resin that on application of load, sudden impact load or gradual loading, that if that can deform, the deformation behavior, that means elongation behavior of that matrix resin, matrix polymer, matrix component gives certain toughness characteristics, because toughness is nothing but the ability to absorb energy by through deformation, resist high temperature and withstand repeated cycling of operations under hygroscopic conditions and prevent or delay onset of micro cracking in the composite. So, polymer matrix can resist degradation at elevated temperature, and that can withstand cyclic load, that means the fatigue property as well as the creep property or the relaxation property of the composite body. All these can be controlled by the matrix resin, so that prevent any micro crack initiation and propagation, so that it does not allow the composite to fail. Now, there can be certain strengths and weaknesses of the matrix resins. There are, this is just this table is not exhaustive, it indicates taking some of a few examples of say thermosets and thermoplastics, say in terms of compounding in the sense, now in a polymer product, a virgin polymer is mixed with certain functional additives, so that it can perform in during processing, fabrication as well as during service period through some chemical reactions, chemical or physical reactions. So, those need to be mixed with the base matrix base polymer. That kind of process is known as compounding. Now, in case of this thermoset polymers, that compounding process is complex, and in case of thermoplastic it is simpler than thermosets. Flow behavior of thermosets are easy, because thermosets polymers are formed from either low molecular analogues or medium molecular analogues to a finally high molecular weight 3-dimensional network, whereas thermoplastics start with very high molecular weight, and that needs very high temperature to soften or to melt, which is actually required during shaping operation or compounding operation. So, that flow characteristics are little difficult, flow behavior is a little difficult as compared to thermosets before its setting. Then fiber impregnation becomes easy in case of thermoset which is difficult in case of thermoplastic, because thermoset starts with low molecular weight prepreg, low molecular weight analog. Similarly, composite processing cycle time is long for thermoset, because one has to allow the chemical reaction to reach the final 3-dimensional network structure, network configuration, whereas in the case of thermoplastic it is short, because on cooling only it can harden, whereas this thermoset hardens due to chemical reaction, which may require a longer period of time. Say in case of epoxy, hardening of epoxy may take 12 to 24 hours, even more than 24 hours, provided it is carried out at ambient condition, ambient temperature, room temperature, but if the temperature is increased, that period of curing can be shortened. But structural properties are good for both. Chemical resistance are also good for these thermosets, but it is little poor in case of thermoplastics. Say you think of the bakelite. Bakelite is a composite of phenol and formaldehyde is the matrix resin. With this wood floor particle is a particulate filler or wood dust, you can say, that is mixed with phenol and formaldehyde resin. Then in along with hexamethylene tetramine known as hexa, this is a cross linking agent. All these three together, when heated at around 150 degree Celsius temperature, say for 5 minutes, provided the thickness is not very high, that leads to a rigid composite, say bakelite switch, electrical gadgets, these are used for with this bakelite material, which is black. Now, that bakelite is stable, is once although it is brittle, if it is not actually broken, but it can serve for a even more than 20-30 years without any loss in their properties, electrical and mechanical properties. So, this way we here it shows a comparison of these strengths and weaknesses of thermosets and thermoplastics in terms of their processing, fabrication and their properties. Once again, let us see how many other polymers are used, or polymers or resins. Actually, polymers are also called resins when we deal with this composite for fabrication of composites. Now, there are as I told earlier, two different categories. In the thermoset categories, we can have epoxies, we can have melamine formaldehyde. Now, melamine formaldehyde is a well known material. Every day we use some crockeries, plastic crockeries, melamine utensils, saucers, cups, dishes, etc., and even cutleries, all these things in general, cutleries, these are made of melamine and formaldehyde. Amine and formaldehyde they combine to form MF resin. This MF resin with some particle reinforcement that can form melamine crockeries. Similarly, phenol and formaldehyde, I will show some reactions how it is formed later. Phenol and formaldehyde resin, polybenzimidazoles, polyimides, that can be aliphatic polyimide or aromatic polyimide, polyesters, mostly unsaturated polyesters, then silicone, CONE here it is wrong, CONE, Then thermoplastics category is nylons, polycarbonates, polyether ether ketone, polyether ketone, polyether sulfones, polyphenylene sulfide. Now, in the thermosetting category, we can have many other polymers. Now, within the epoxy resin category, we can change the number of functional sites of epoxies, so that one can tailor the ultimate or final properties of the epoxies. I will show you how it actually changes by changing the functionality of epoxy resins. It can be difunctional, it can be tetrafunctional. This way we can say we can have different categories like difunctional category epoxy, polyfunctional category epoxy resins. Then phenolic resins we can have in different form, Novolac, which is solid in thermoplastic stage, as a Resol it is water based, is also phenol formulated resin. So, this Novolac can be used in one process, one kind of processes for making composite. These Resols are used as adhesives or liquid resins for making laminates and composites. Say commercial laminates, commercial plywoods, for those making commercial plywoods, those are also composite, where wood veneers are assembled with the help of this phenol formulated resin. In this in that product, these Resols are the only choice for giving very good bonding between the wood veneers inter or laminates and forming a very strong and rigid composite. In the polyimide category, these are there can be condensation polyimide, addition polyimide and bismalimides. In the thermoplastic resin category, the use of engineering thermoplastics as matrices originated with a view to realize low cost manufacturing, low cost composite manufacturing. Now, in this taking this engineering thermoplastics, the factors contributing to this objective are long pre-peg stability. Now, let me explain what is called pre-peg. Basically these composites are made from rovings, fabrics, etc. So, the clothes, oven fabric. Now, those oven fabrics are soaked with the resin in green condition. So, that after soaking, then if there is some solvent is removed or dried. So, that resin soaked fabric is known as pre-peg. Then those pre-pegs can be assembled, number of pre-pegs can be assembled to give a thicker composite. So, that your self stability of pre-peg is important. Now, these pre-pegs are pre-pegs containing this resin, it is in reactive condition, that means it is reactive. So, it should be properly stored either in refrigerated condition or in ambient condition. We have to see how it is reactive and how long it can remain stable. Say for example, the epoxy resin, I tell you, epoxy resin ultimately it leads to a thermoset, it is a thermoset product. Initially epoxy resin is liquid, it is available in the liquid form, in the reactive liquid form. Since it is in the reactive liquid form, when it it is mixed with curing agent, epoxy curing agent or cross linking agent, this starts reacting immediately with the curing agent and starts changing its viscosity, and gradually it hardens and ultimately it becomes solid. Now, since this resin, epoxy resin, is in reactive liquid form, slowly without the curing agent, slowly it increases its viscosity, and which will become unsuitable for its application. So, this aspect is known as the stability of the resin as well as the prepeg. Now, in industrial practice, what happens? It is not that only a few such fabrics are soaked with the resin, and those are immediately assembled and placed under the hot press for making the composite. It is not like that. In one shop, such prepegs are prepared in huge quantity, which is shifted to the other molding shop, where it is compression molded. So, there can be some piling up of this prepeg sheets, and which should remain stable without changing any properties, because during compression this prepeg material containing the resin, that must melt and show some flow characteristic under application of heat and pressure, so that it can give a through resin flow that can give, provide very good consolidation and binding of the several layers. So, that is called prepeg stability, and it is better in industrial practice to save energy and to minimize the cost of the product. The prepeg should remain stable at ambient condition. It should not require refrigerated storing. Then first processing cycle. Now, these composites are made by after soaking the resin to the fabric, then assembling, then putting in the mold and hot pressing at elevated temperature. Now, the such curing cycle, or starting from prepeg to the curing and cooling cycle, cooling stage, the time requirement should be as minimum as possible, so that the productivity of the composite will be high. That is, in other way, the processing cycle should be minimum, so that it can provide high productivity to have maximum profit. Then ease of quality control. Ease of quality control in the sense that each and every batch should be uniform in properties. After analysis and testing, it is evaluated, the properties of the composites or products are evaluated, and that should not be very lengthy. Only 1 or 2 representative tests should be sufficient to indicate the quality of the composite product made. Then ability to reprocess the components to remove imperfections. Reprocessing of components, say if there is some imperfection is found in a composite item fabricated, that can be a huge item. So, it cannot be totally discarded or disposed of, but it can be repaired, so that the imperfection which has been found in the product can be removed. That ability, that provision, that ability should be there in the product. High damage tolerance characteristics, these also should be considered. The candidate polymers used as matrix resin may be classified as, in this thermoplastic resin category, polyaryl ethers, imides, amide imides, polyaniline sulfides. These are of high performance category matrix resins, thermoplastic matrix resin. High performance in the sense, these matrix resins leading to some composites which are supposed to withstand very high temperature and very strong. Say, one can say This can be considered as engineering thermoplastics, and these engineering thermoplastics can give very good high performance composites. As I was talking about the functionality of the epoxy. So, here this structure or formula you can say shows a difunctional epoxy resin. This is a diglycidyl ether of bisphenol A. This is the bisphenol A moiety. This is the bisphenol A moiety, and this is the epichlorohydrin moiety. So, this reacts with epichlorohydrin reacts with bisphenol A on the both sides and forming a polymer chain. Now, these are the reactive sites of this epoxy resin, and bifunction, here is one functionality reactive, here is one functional reactive in the polymer chain. So, this is called bifunctional reactivity. So, by virtue of this bifunctional reactivity, it can give a linear polymer leaving behind some reactive site which remains dormant, and when some cross linking agent is mixed with this thing, it form a 3-dimensional network structure. So, here this molecular weight of this polymer can vary. So, here you see the value of n can vary from 0.2 to 12, corresponding to number of average molecular weight of about 400 to 4300. So, depending on the nature of composite to be prepared, one can judge to what length this polymer can be formed, so that good strength properties or performance properties could be available. Next is the multifunctional. Beyond difunctional, we call it multifunctional epoxy. Now, in that case, epoxy resin is actually coupled with Novolac. Phenol Novolac originates from phenol and formaldehyde. It is one grade of phenol formaldehyde resin, thermoplastic grade of phenol formaldehyde resin. So, this this is actually phenol moiety. This is another phenol moiety. So, these are reacted with formaldehyde, forming this methyl link through methyl linkage and epichlorohydrin. So, epichlorohydrin, phenol, formaldehyde, all these three compounds together form a polymer, giving a phenolic resin functionalities or phenolic resin properties, as well as epoxy resin characteristics and functionalities, and that gives the advantage of epoxy resin as well as that of phenolic resin, and these resins result from the reaction of epichlorohydrin with the Novolac or phenolic, bearing 2 to 5 epoxy functionalities per molecule on an average. They are capable of yielding highly cross-linked systems possessing higher glass transition than the bisphenol epichlorohydrin based epoxy. So, when one needs higher glass transition characteristics of the composite, they can blend Novolac along with the epoxy system. Thank you.